Tonight, we're going to explore one of the most underestimated challenges in all of spaceflight. This year, NASA announced plans for a permanent human base on the moon. To most people, it sounded like the next logical step in space exploration. After all, we've already landed there. So how much harder could it really be? The answer isn't getting there. It's surviving after you arrive. Landing on the moon and living on the moon are two completely different challenges. The Apollo astronauts stayed for hours, sometimes days, before returning home. A permanent base doesn't have that luxury. It has to survive, day after day, in one of the most hostile environments humans have ever encountered. Because the moon never stops fighting back. Its dust is sharp enough to work its way into machinery and grind away at moving parts. The vacuum attacks every seal. Temperatures swing by hundreds of degrees. Radiation arrives with almost nothing to stop it. Gravity is too weak to keep the human body healthy. And after weeks or months, even the isolation itself begins to take its toll. None of these threats works alone. Together, they wage a relentless war against every spacesuit, every habitat, every machine, and every astronaut who tries to call the moon home. By the end of tonight, you'll understand why building a permanent lunar base is a fundamentally different challenge from simply landing on the moon, how each of these invisible threats slowly pushes both people and technology to their limits, and what NASA's plan is really asking of the people who will one day live there. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. On March 24th, 2026, NASA held a press event called Ignition. The name was deliberate. The message was unmistakable. Administrator Jared Zachman stood before cameras and announced that the Artemis program was being restructured around a single, explicit goal: a permanent base near the lunar South Pole, not a temporary outpost, not a brief visit followed by a long absence. A base, phased, continuously expanding, designed to support human crews for months and eventually years. The commitment was $20 billion over 7 years, distributed across 3 phases and stretching into the early to mid-2030s. Zachman framed it without hesitation. America, he said, would never again give up the moon. 2 months later, on May 26, 2026, NASA awarded the first contracts. Blue Origin received the anchor assignment, building the Mark I Endurance lander, the vehicle that would deliver the first hardware for what NASA was already calling Moon Base 1, targeted for launch no earlier than fall of that year. Astrolab and Lunar Outpost were brought in for rovers. Firefly Aerospace would handle orbital relay infrastructure, the communication backbone the base would depend on from day one. The architecture described in those contract documents was not a single structure. It was a distributed network spread across hundreds of square miles of the South Pole region. Habitats, science stations, power generation units, roads, communication relays, rover garages, and a fleet of autonomous hopping drones called Moonfall, designed to move small payloads across the surface without needing roads at all. The base would not be one thing in one place. It would be a permanent, self-reinforcing presence across an entire region of the moon. The timing followed directly from recent progress. Just before the May contracts, Artemis II had completed its mission. 4 astronauts flew around the moon and returned safely, validating the Orion capsule, the Space Launch System, and deep space life support systems across a real mission profile. Artemis III was restructured as an orbital docking test, planned for 2027. Artemis IV, planned for 2028, would attempt the first crewed lunar landing since 1972. After that, NASA planned to land crews every 6 months, each rotation adding infrastructure, each wave pushing the base closer to continuous human occupation. Public coverage was immediate and enthusiastic. Animations showed habitats perched on crater rims above permanently shadowed valleys. Infographics traced neat arrows from Earth to lunar orbit to the South Pole. Social media ran ahead of the engineering and started imagining what came after habitats. Lunar greenhouses, pressurized recreation spaces, Someone suggested lunar pizza restaurants. The excitement was genuine, and it was aimed at the wrong thing. Because here is the question that was not being asked in the press conferences. Not in the animations, not in the contract announcements, not in the infographics. We can land on the moon. We have done it. We are building the systems to do it again. We can build a structure there. Engineering firms are already designing the modules, the power systems, the regolith shielding. The hardware exists or will exist. Landing and construction are problems we know how to approach. The harder question is what happens after the structure arrives? What happens when you try to keep it functioning? What happens when you try to keep people alive inside it? Not for a weekend or a week, but for months, for years. Continuously? What happens when the environment outside the airlock is not a backdrop for photographs, but a constant operating force acting on every seal, every joint, every circuit, every biological system, every single day, without pause, without mercy, without the option of declaring the experiment over? There is a useful way to think about this. Visiting a place and living in a place are not the same kind of problem. A visitor tolerates conditions. A resident has to survive them, over and over, across time. The moon does not offer a grace period. It does not ease you in. The same forces that act on a structure on day 1 are still acting on it on day 300. And they are not neutral forces. They are some of the most extreme physical conditions anywhere in the inner solar system. The press conferences described a destination, a place to reach, a structure to build, a flag to plant. That framing is natural. It is how exploration has always been announced. But it quietly leaves out the part that comes after arrival, the part that does not compress into an animation or an infographic, the part that has no dramatic moment, no single mission patch, no launch broadcast, just the slow, continuous obligation to keep a human outpost alive against an environment that never stops. The announcement in 2026 was real. The commitment was serious. The engineering is underway. But the challenges that will determine whether Moonbase 1 becomes a permanent human presence or an abandoned structure on a crater rim have almost nothing to do with the launch date or the contract value. They have everything to do with what the moon does to things that try to stay. And that part has barely started to be understood. To see why staying is so hard, start with the ground it has to stand on. The moon most people picture is a place of austere beauty. Craters and silence and grey dust under a black sky. That image is accurate as far as it goes. But the moon the engineers are planning around is something different. It is the moon the Apollo astronauts came back describing. The one that cracked equipment, fouled seals, jammed mechanisms, and cycled through temperature extremes that no Earth-built material was designed to endure. The textbook moon is a destination. The engineering moon is an adversary. Start with the atmosphere, or rather the absence of one. The absence. This fact gets repeated so often that it has stopped registering. No atmosphere. Everyone knows it. It sounds like a breathing problem, something solved with a good helmet and an oxygen tank. But the breathing is actually the easy part. The consequences that follow from no atmosphere are far worse than the air problem, and they operate on every system, every surface, every structure, at every moment. No atmosphere means no air pressure outside, none, which means every habitat is a pressure vessel, holding breathable air against the vacuum pressing in from the other side. The differential is roughly the same pressure as a car tire, acting on every square centimetre of every wall, every window, every joint, every seal, continuously. 24 hours a day, for years. Think about what that means at the level of a single floor. A small crack in the wall of a house on Earth produces a draft. Cold air seeps in. You notice it. You seal it. Nothing catastrophic happens. A small crack in a habitat wall on the moon does not produce a draft. It produces explosive decompression. The air inside does not seep out. It escapes into a vacuum that has no back pressure, no friction, no atmosphere to resist the rush. There is no margin between a minor structural flaw and a lethal one. Every seal, every joint, every airlock hinge, every viewport frame is a potential point of catastrophic failure under continuous mechanical load. Not for a few critical minutes during a launch. continuously, for the entire duration of the mission. But something else is happening. The pressure problem is severe. The thermal problem may be worse. On Earth, the atmosphere is not just something you breathe. It is a massive heat transfer system. Air carries warmth from place to place, wind mixes thermal layers, clouds intercept sunlight and moderate surface heating. Humidity stores and releases heat, smoothing the extremes. The result is that Earth's surface temperature changes slowly, predictably, within a range that life and most engineering can tolerate. On the Moon, none of that exists. Heat can only move by two mechanisms: radiation, which is the surface emitting energy as light, and conduction, which requires direct physical contact between materials. No convection, no insulating gas layer, nothing to moderate the swings. At the lunar equator, surface temperatures reach 100 to 27 degrees Celsius in direct sunlight. When the sun goes down and the 2-week lunar night begins, that same surface drops to negative 173 degrees Celsius. That is a range of 300 degrees, cycling every 29.5 Earth days. No material used in ordinary construction is designed for that. Metals expand and contract. Seals that are tight at one temperature leak at another. Electronics calibrated for a narrow thermal band drift out of tolerance. Structures stressed in one thermal state carry those stresses forward into the next. The South Pole changes this thermal regime. It does not solve it. At the South Pole, the sun never rises more than a few degrees above the horizon. The sun grazes the surface at an oblique angle, and at certain elevated ridges near craters like Shackleton, that grazing light is nearly continuous for much of the lunar year. Temperature swings are less extreme than at the equator. That is precisely why NASA chose the South Pole. It gets chosen for two reasons, and they are both real, and they both come with traps attached. The first is light. Crater rims near Shackleton and the connecting ridge that extends toward De Gerlache crater, and elevated terrain near Malapa Mountain to the south, receive sunlight 80 to 90% of the year. For a base that depends on solar power, that is the best anywhere on the Moon. Even here, though, the sight is not perfect. Shadow periods still occur. Some last several consecutive Earth days. During those gaps, power generation drops and the base must live on stored reserves, a problem that compounds if something else goes wrong at the same time. The second reason is ice. Permanently shadowed craters near the South Pole have walls that never see sunlight. Temperatures inside them approach what you would find in deep space. Over billions of years, water delivered by comets and asteroids has accumulated in those cold traps, preserved by permanent darkness. Orbital instruments confirm the ice is there. But here's where it gets strange. Orbital instruments can confirm presence. They cannot confirm concentration. The ice might exist in thick, mineable deposits. It might also be dispersed so thinly through the regolith, the loose surface material, that extracting a useful quantity would consume more energy than the water is worth. Whether the South Pole's most valuable asset is a transformative resource or a logistical mirage is a question that will not be answered until machines actually dig. The site was chosen partly on the promise of that ice. Whether the promise is real remains unknown. And the South Pole introduces problems no one at the equator faces. The sun never rises high. Lighting is permanently oblique. Long shifting shadows stretch across every surface at shallow angles, making it difficult to read terrain and navigate safely. Crew members and rovers operating in that environment are not working in clear sunlight. They are working in perpetual low-angle twilight, where shadows hide drop-offs and surface features become ambiguous. Communication compounds this. From the South Pole, Earth hangs very low on the northern horizon, sometimes barely above it. Local terrain, a ridge, a crater wall, a modest boulder field can block line of sight entirely. A crew member on a crater floor has no direct contact with Earth. The ISS handles this through TDRS satellites, tracking and data relay satellites, positioned in high geosynchronous orbit, above the equator, always visible from the station's position. The South Pole base cannot replicate that geometry. No satellite positioned for that kind of continuous coverage exists yet. and the terrain blocking is local and variable. The base needs a relay infrastructure, orbital satellites positioned specifically for lunar polar coverage, or networks of communication towers placed on the elevated terrain around the base, or both. Firefly Aerospace's contract includes precisely this orbital relay work, which means another parallel program must be launched, deployed, maintained, and eventually replaced, a separate infrastructure dependency running alongside everything happening on the surface. Then, there is the ground itself. The ridges near Shackleton that carry the best illumination are narrow. The zones where sunlight, stable footing, acceptable slope, communication line of sight, and proximity to the ice deposits all converge simultaneously are not large plateaus. They are strips a few hundred meters wide in places. Onto those strips, the base must place habitats, solar arrays, thermal radiators, rover parking, construction staging areas, dust berms, and eventually a nuclear reactor with a 90-meter radiation exclusion zone around it. Every placement affects every other placement. A rover driving between the habitat and the solar array kicks dust onto the panels. Thermal radiators must face away from the sun to shed heat, but cannot face into the reactor exclusion zone. Construction staging must be close enough for crew access during EVA, an extravehicular activity, a spacewalk, but far enough that disturbed dust does not contaminate airlocks. The shadow cast by one structure falls on a neighbor's solar array. The layout is not a planning exercise. It is a constrained optimization problem where every decision propagates through power, thermal, dust, communications, and safety simultaneously. On Earth, you can move a building. On the Moon, a landed asset stays where it lands unless you have heavy equipment capable of moving multi-ton structures. Equipment that itself requires power, maintenance, and dust management. Getting the layout wrong in Phase 1 means Phase 2 inherits those mistakes and cannot undo them. The site was chosen for its advantages, and the advantages are real, but each of them arrives with a shadow attached. The full weight of what those shadows mean, in power and heat and mechanical failure, is only beginning to come into focus. One of those shadows has a name. It coats everything on that narrow ridge. It gets into every joint, every seal, every breath. It is not a metaphor. It is dust. Every Apollo astronaut came home with the same warning. Not about the silence, not about the isolation, not about the strange horizon or the slow fall of steps in low gravity. The dust. Eugene Cernan, the commander of Apollo 17 and the last human to walk on the moon, called dust one of the most serious problems on the lunar surface. Harrison Schmitt, the geologist on that same mission and the only trained scientist to walk on the moon, developed an immediate respiratory reaction within hours of his first moonwalk. Swollen nasal passages, a burning throat, clogged sinuses that persisted for hours after he returned to the cabin. He called it lunar hay fever. And Schmitt was not alone. All 12 men who walked on the moon experienced some version of that reaction, every one of them, during stays that lasted between 22 and 75 hours on the surface. The longest single excursion outside, a single EVA, came in at 7 hours and 37 minutes. That is important. These were brief visits, and they were still enough. Astronauts brushed their suits before climbing back through the hatch. The brushing helped. It removed perhaps half the visible material. The rest stayed. Dust-coated visors so thoroughly that visibility degraded. It clogged the wrist joints and gloves, adding resistance to every movement. It infiltrated every seal and zipper. Boot soles wore through faster than expected. Fabric layers frayed. Once the crew repressurized and removed their helmets, the dust that had ridden in on the suits became airborne again inside the cabin, entering lungs, settling in eyes, finding its way into instrument panels and connectors. Apollo could absorb all of that. It could absorb it because Apollo left. Crews returned to Earth within days. Suits were retired. Landers were abandoned on the surface. Every piece of dust-degraded hardware was simply left behind. A permanent base does not have that option, not even close. Suits must be reused hundreds of times. Airlocks must cycle thousands of times. Habitats must hold dust out across years of continuous occupation. The damage that Apollo spread across a few dozen hours of total surface time, a base would accumulate on a weekly basis, indefinitely. And to understand why that matters, you have to understand why lunar dust is not like any dust on Earth. Earth dust is old and tired. It has been worn down by billions of years of wind, water, and chemical weathering. The particles are rounded, smoothed, softened. They brush off clothing. They wash off skin. They can be swept and vacuumed and dissolved. The moon has none of those processes. No wind, no water, no chemical weathering. The moon's surface material is made almost entirely by violence. For more than 4 billion years, micrometeorites have been striking the lunar surface at speeds of tens of kilometers per second. These are not gentle collisions. They shatter rock into fragments of every size, from boulders down to particles smaller than a single cell. The smallest, below 20 micrometers in diameter, are what scientists formally call lunar dust. Roughly the width of a human hair cut into 5 equal slices. Under an electron microscope, these particles look nothing like grains of sand. They look like shards of broken glass, fractured, angular, jagged. Their edges are sharp enough to cut biological tissue at the cellular level. That is not a figure of speech. The morphology of lunar dust is genuinely sharp, in a way that Earth particles are not. But the shape is only the beginning. The solar wind, a constant stream of charged particles flowing outward from the sun, continuously bombards the lunar surface. It implants ions into the dust and strips electrons away, leaving the particles electrostatically charged. On Earth, humidity in the air dissipates static charge almost immediately. The moon has no humidity. The charge persists indefinitely, and charged particles cling. They cling to metal, glass, fabric, skin, and polymer, with a tenacity that mechanical brushing simply cannot overcome. That is why Apollo's brushing only removed half the dust. The other half was not stuck because of gravity. It was stuck because of charge. Chemistry adds a third layer. Regolith is roughly 50% silicon dioxide by weight, with iron oxide and calcium oxide making up most of the rest. The fracturing process, billions of years of constant impact, continuously exposes fresh mineral surfaces. Fresh surfaces that have never encountered oxygen, never encountered water. They are chemically reactive in a way that aged, weathered Earth minerals are not. When those surfaces encounter moisture inside a pressurized habitat, the moisture from breath and sweat and skin, they can generate free radicals, highly reactive molecular fragments that attack biological tissue. Research using lunar simulant, material engineered to replicate the properties of lunar regolith, has shown that prolonged exposure destroys lung cells and brain cells under laboratory conditions. The particles are small enough to pass through the respiratory system's filtering mechanisms entirely, traveling deep into the lungs and lodging in the alveoli, the tiny sacs where the lungs exchange oxygen and carbon dioxide with the blood. Once there, they cannot be expelled. The body has no mechanism to clear particles that small from that deep. Their sharp edges and reactive surfaces cause chronic inflammation that does not resolve because the source never leaves. The long-term health consequences of months or years of this exposure are genuinely unknown. No human has been exposed for that duration. But the evidence from Apollo, from simulant studies, and from decades of research into terrestrial silica exposure suggests the risk is serious. In March 2025, NASA demonstrated an electrodynamic dust shield on the lunar surface. A small experimental unit, delivered by a commercial lander, used alternating electric fields to lift and repel charged dust particles from glass and thermal radiator surfaces. It worked. The results were genuinely encouraging, a real advance in the decades-long effort to address this problem. But the picture did not hold. A dust shield that protects flat glass panels does not protect suit joints. It does not prevent dust from entering airlocks as crews pass through. It does not protect ventilation filters, sample storage, drill mechanisms, or rover bearings. The shield is narrow by design. It targets specific surfaces. The surfaces that actually matter most for long-term survival are precisely the ones it cannot reach. Think about the operational reality. Every time a crew member exits the habitat, dust enters the airlock. Before repressurizing, the crew member attempts to brush and clean. Some dust stays. It comes in. Ventilation systems run continuously to filter that dust from the cabin air, and the filters themselves degrade under constant abrasion. Those filters must be replaced. Manufactured on the moon or launched from Earth at enormous cost, either way. Outside, rovers accumulate dust on every bearing and every sensor. Drills clog. Sample containers seal imperfectly. Construction equipment develops resistance in every connection. The base would require a daily dust management protocol, not a monthly deep clean. Daily. Because the moon does not take days off from producing dust. Every footstep in low gravity kicks particles that travel far higher and settle far more slowly than anything behaves on Earth. Vehicle traffic raises plumes that travel kilometers before settling back to the surface. And without human activity, dust still moves on its own. Near the terminator, the boundary between sunlit and shadowed terrain, differential electrostatic charging between lit and dark surfaces, creates electric fields strong enough to levitate dust particles against the moon's weak gravity. The particles lift off and migrate without any wind at all, without any impact, simply because the charge differential is strong enough. This is not a theoretical concern. It has been observed from orbit, and a South Pole base sits precisely at the terminator. The base would be built exactly where that effect is a continuous background condition, not an occasional event. Dust moving on its own all the time at the exact location the base must occupy. There is no solving this. There are only ways to manage it. Management is permanent. It competes for crew time, equipment resources, and spare parts with every other demand the base makes. And those other demands are considerable. Dust is not a hazard you overcome during construction and then leave behind. It is a tax paid every day for as long as the base exists. That tax was affordable for 12 men who stayed a few days and came home. For a crew living there, it is a continuous operational burden with no expiration date. And dust was only the first item on the surface's account. The dust is not the only thing working on that hardware day and night. Two more forces are acting on every surface, every joint, every seal, every wire the moment it is placed there. They are quieter than dust. They are slower than dust. And in some ways they are more dangerous, because they work from inside the material itself, at the level of molecules and crystal bonds, in ways that leave no visible trace until something fails. The first is heat, or more precisely, the absence of any stable temperature at all. Sunlit surfaces at the lunar South Pole can exceed 100 degrees Celsius. Nearby shadowed areas can drop below -70 degrees. That range alone sounds punishing, but that is not the real problem. The real problem is the transition. On Earth, the atmosphere buffers temperature change. Air conducts heat, distributes it, slows the swing. The moon has none of that. When a surface moves from sunlight into shadow, the temperature does not drift gradually downward over hours. It drops. A surface baking at 100 degrees can begin plunging toward -100 degrees within minutes of losing direct sun. When the sun returns, the reversal is just as sharp. The material goes from contracting to expanding and back again, repeatedly, with almost no damping. This matters because every material responds to temperature change differently. A metal rod expands when heated and contracts when cooled. That much is basic physics. But a structure made of two different metals expands at two different rates. Think of two metal strips bolted together at room temperature. Heat them, and each strip wants to grow by a slightly different amount. They pull against each other. Cool them rapidly, and the same fight runs in reverse. Now do that thousands of times. The ISS manages this too. Its orbital period is roughly 90 minutes, so it cycles between sunlight and shadow about 16 times per day. That is already demanding. But the South Pole is different. Some sites cycle slowly as the sun traces its shallow arc across the horizon over days. Others cycle rapidly, the sun dipping behind a ridge and reappearing within minutes, whipsawing surfaces through their full thermal range dozens of times in a single Earth day. Equipment at those sites could experience thousands of thermal shocks per year. Each one slightly loosens a joint. Each one slightly propagates a crack. Each one slightly degrades a seal. Seals that hold perfectly at 20 degrees Celsius develop microscopic gaps at negative 150 degrees. Welds that pass inspection at room temperature crack after hundreds of cycles between extremes. This is not speculation. It is standard material science. It is why every long-duration space structure requires significant overdesign to survive it. And then the second problem arrives. The heat itself is also a problem, because on the moon, there is no way to move it. On Earth, electronics are cooled by fans, by airflow, by the simple fact that heat conducts into moving air and carries away. In vacuum, convection does not exist. Heat can only leave a surface in two ways. Radiation, which requires panels facing empty space and grows very slowly with temperature or conduction into the regolith beneath. Lunar regolith is a poor conductor. Heat moves through it sluggishly. So keeping electronics cool on the moon requires dedicated radiator panels, large flat surfaces oriented away from the sun and toward the sky, doing nothing but radiating waste heat into space. Those panels must be kept clean to radiate efficiently. Dust degrades them. Micrometeorites pit them. Thermal cycling stresses their mounting structures. If their efficiency drops, heat builds inside the system. Electronics overheat. Lubricants break down faster. Mechanical systems begin to seize. The dust problem and the heat problem are not independent. They feed each other. And cooling is only one half of the thermal challenge. The other half runs in the opposite direction. When a South Pole site enters shadow, everything radiates heat outward and nothing replaces it. Batteries lose capacity in the cold. Lubricants thicken and eventually stop moving entirely. Below certain temperatures, the substrates inside electronics become brittle, and solder joints crack as they contract. Keeping a habitat warm through a shadow period that lasts several Earth days requires continuous power for electric heaters. That power cannot come from solar panels in shadow. It must come from stored reserves or a non-solar source. The thermal problem and the power problem are the same problem, viewed from two different angles. Now add vacuum. Vacuum is not merely the absence of air. It is the condition that removes every buffer between a material and failure. On Earth, metal surfaces oxidize. A thin layer of oxide forms on every exposed piece of iron, aluminum, copper. That layer is protective. It prevents the underlying metal from bonding to adjacent surfaces. In vacuum, that oxide layer does not form, or it is slowly sputtered away by micrometeorites and charged particles. What remains is bare metal. And bare metal in contact with other bare metal does something unexpected. It welds. The atomic bonds between two touching metal surfaces form spontaneously, because nothing is stopping them. The parts were designed to move freely. They no longer can. This is called cold welding, and it is not a theoretical concern. Multiple satellite solar array deployment mechanisms have experienced it after prolonged vacuum storage. Hinges fused. Arrays that were supposed to unfold did not. Engineers had to redesign mating surfaces with anti-galling coatings for subsequent missions. On a lunar base, every hinge, every drill mechanism, every rover joint, every piece of construction equipment operates in that same environment, continuously. Vacuum also runs a slow chemistry on polymers, seals, gaskets, cable insulation, window coatings, the flexible connectors on suit joints. Under Earth conditions, these materials last decades. Under combined vacuum, ultraviolet exposure, charged particle bombardment, and thermal cycling, laboratory testing with simulated lunar conditions has demonstrated measurable embrittlement within months. The material grows rigid. It cracks under stress it would once have flexed through easily. A seal that was pliable during installation has become brittle by the end of the first year. There is no visible warning. The failure is internal, at the molecular level, until the day it propagates to the surface, and lubricants outgas. The volatile components in a lubricant, the light organic molecules that keep it fluid and slippery, escape into vacuum molecule by molecule. The process is silent and invisible. But after months of operation, the joint that ran smoothly during the first week begins to resist. By month 6, it may seize entirely. Replacing it requires an EVA. Suit up, cycle the airlock, step outside, work in radiation and dust, bring more dust back in on the suit, and spend hours on a task that would take minutes in a workshop. This is the cost multiplier of vacuum. Every maintenance action that would be routine on Earth becomes an expedition. Wait, consider what the ISS tells us about SEAL management at scale. The ISS is arguably the most carefully engineered pressurized structure ever built. It operates in microgravity, which reduces mechanical stress on SEALs. It carries no surface dust. Its thermal cycling, while demanding, is more predictable than the lunar South Pole. Despite all of that, air leaks are a recurring operational concern. One leak in the Russian Zvezda module persisted for years. The source was identified after months of detective work, but secondary cracks kept appearing. Crew members spent hundreds of cumulative hours managing that single leak. Ultrasonic inspections, temporary sealant applications, isolation of entire compartments. The ISS carries a crew of 6 or 7 people, rotated every 6 months, with regular resupply and ground support. A moon base. One crew is 4 people. One persistent leak on a 4-person base does not consume a small fraction of crew capacity. It consumes a quarter of it, for months. And a lunar base faces conditions no ISS SEAL has ever faced. Every airlock cycle admits dust to the SEAL surface. Every cold period thermally contracts the housing around that SEAL, opening microscopic gaps that slightly increase the leak rate. For a 4-person crew conducting regular EVAs, an airlock might cycle twice per person per day. That is roughly 8 cycles per day, roughly 3,000 cycles per year. Each cycle is a pressure flexion, an abrasion event, a dose of thermal stress. No airlock seal in the history of spaceflight has been tested at this combined rate and duration. Service life is genuinely unknown. The answer matters enormously because it determines how many replacement seals must be stocked, how often crew must perform pressure-critical replacements, and whether a slow cumulative leak rate across dozens of seal interfaces becomes a significant consumable drain over months of operation. A slow leak is not immediately catastrophic. Habitats carry reserve air, but every leak is atmosphere that must be replaced. Over years, cumulative loss across dozens of penetrations in the pressure envelope, every airlock, every window frame, every cable pass-through, every equipment hatch could become a meaningful logistics problem. And a leak that cannot be located quickly forces isolation of modules, reduces living space, and crowds a crew that is already living in close quarters with no easy exit. A rapid decompression is a different category entirely. A micrometeorite puncture, a fatigue crack reaching the surface, an airlock mechanism failing in a partially open state. Any of these gives the crew minutes to respond. Not hours, minutes. Emergency procedures require immediate access to pressure suits and redundant sealed compartments, so that losing one pressurized volume does not mean losing everything. That redundancy adds mass to the structure, complexity to the systems, and cost to every mission that supplies it. All of this, the thermal cycling that fatigues every joint across thousands of shocks per year, the vacuum that outgasses lubricants and embrittles polymers, and cold welds metals together at every interface, is happening continuously from the moment equipment is placed on the surface. It does not pause during operations. It does not slow during periods of low activity. It continues through every shadow, every sunlit period, every EVA, every meal, every sleep cycle. The dust taxes the surface. The heat and cold tax the materials. The vacuum taxes the chemistry. And all three draw from the same account, the power that keeps any of it manageable. That account has its own limits, and they are closer than the early plans suggest. That account is power. Everything else draws from it. Not one system among many. The foundation. Without continuous, reliable electrical power, nothing on the lunar surface functions. The habitat cannot maintain pressure. Thermal management cannot reject heat or provide warmth. Dust mitigation systems stop. Air recycling stops. Water processing stops. Every threat covered so far, the dust accumulating on every surface, the thermal cycling fatiguing every joint, the vacuum chemistry attacking every material, all of it becomes unmanageable the moment power fails. Losing power on the moon is not like losing power on Earth, where you light candles and wait for the utility crew. Losing power on the moon means losing life support. The margins are measured in hours, not days. Hours. This is why South Pole site selection was driven, more than by anything else, by access to sunlight. The elevated ridges near Shackleton crater receive solar illumination roughly 80 to 90% of the lunar year. That figure is extraordinary. It is the best solar availability anywhere on the moon. At equatorial sites, the 2-week lunar night makes solar power unworkable as a primary source entirely. The South Pole's ridges solve that, but 80 to 90% is not 100%. Even the best sites have shadow periods, and during those periods, the base must survive on stored energy or an alternative power source. Researchers working on lunar surface power have described this problem plainly. Lunar night energy storage is probably the most demanding energy storage challenge in solar system exploration. Here is the arithmetic. A minimal 4-person base requires roughly 25 to 30 kilowatts of continuous electrical power to maintain life support, thermal management, lighting, communications, and computing. Some analyses, including ones that account for active external thermal management and partial in-situ resource use, push that figure to around 65 kilowatts. Take the lower estimate, 25 kilowatts, sustained through a 4 Earth day shadow period. That requires 2,400 kilowatt hours of stored energy. The best space-grade lithium-ion batteries store around 200 watt-hours per kilogram at the cell level. That is the theoretical optimum before real engineering enters. Account for packaging, thermal management hardware, charge controllers, and structural mass, and the realistic system-level energy density drops to around 150 watt-hours per kilogram. To store 2,400 kilowatt-hours at 150 watt-hours per kilogram, you need 16,000 kilograms of batteries, 16 metric tons. That is roughly the entire payload capacity of a large lunar lander, devoted to nothing but batteries for a single 4-day shadow period. And the picture gets worse. That calculation assumes the batteries perform at full rated capacity. In extreme cold, they do not. Low temperatures reduce lithium-ion output by 30 to 50%, unless the battery packs are actively heated. And heating them consumes power drawn from the same reserves the batteries are supposed to be providing. The system partially defeats itself. No battery chemistry currently in production, and none in advanced development, makes these numbers work at acceptable mass. Researchers have explored alternatives. Regenerative fuel cells store energy as hydrogen and oxygen, then recombine them electrochemically to generate power on demand. The energy density is higher than lithium-ion at the system level, but regenerative fuel cells introduce mechanical complexity that batteries avoid. Pumps, membranes, pressure management, consumable gases that must be tracked and replenished, and failure modes at every step. Every storage approach trades one constraint for another. None of them eliminate the underlying problem. Darkness on the moon lasts long enough to exhaust any practically deliverable chemically stored energy supply. This is why NASA's plan explicitly includes nuclear power. Phase 2 of the base development calls for radioisotope thermoelectric generators, known as RTGs, to demonstrate nuclear capability on the surface. RTGs convert heat from slowly decaying radioactive material into electricity. The technology is proven across decades of deep space missions. Voyager, Cassini, Curiosity, Perseverance, all have operated on RTG power far from the sun. But an RTG's output is measured in hundreds of watts. A base needing tens of kilowatts would require a quantity of RTGs, whose combined mass and complexity make them impractical as a primary solution. RTGs are a demonstration step, not the answer. The answer, as NASA and the Department of Energy have pursued it, is a surface fission reactor. The kilopower concept and its successors are designed specifically for this purpose. A compact fission system capable of producing at least 10 kilowatts of electrical power, enough for basic life support through extended darkness. That program is in active development, but a fission reactor on the lunar surface brings its own set of constraints. A reactor requires a radiation exclusion zone of roughly 90 meters around it, with proper regolith shielding, before the zone closest to the base can be used safely. That constraint was already mentioned in the context of base layout. It is worth dwelling on what it means operationally. The reactor sits at a distance from the habitat, connected by power cables crossing terrain that must itself be managed. And the exclusion zone shapes every decision about what can be placed where. The reactor also requires cooling. In vacuum, there is no convective cooling. Heat must be shed through radiator panels, and radiator panels are flat surfaces in a dust environment, subject to the same accumulation and degradation that affects every other surface system. If dust degrades radiator efficiency, the reactor must throttle down to avoid overheating. The reactor's cooling infrastructure and the dust problem are not separate issues. They are the same problem appearing again in a new form. Then there is maintenance. A fission reactor on the lunar surface must either achieve extraordinary reliability across years of operation without servicing, or it must be designed for robotic or crew maintenance. Every maintenance task on the moon is harder than on Earth. The suits, the radiation environment, the dust, the temperature swings, every factor compounds the difficulty. And then there is the matter of regulatory and political approval to launch nuclear material from Earth. That process adds programmatic complexity and potential delays to a timeline the rest of the base development already depends on. None of this means nuclear power is the wrong choice. It means nuclear power is the only credible choice, and even the only credible choice has costs. Solar panels remain part of the plan, particularly in the early phases, but solar faces every force already catalogued here. Dust accumulates and cuts output. Electrodynamic shields help but consume power and protect only flat surfaces. Thermal cycling stresses mounting hardware and electrical connections. Radiation degrades photovoltaic cell efficiency over time. The low sun angle at the South Pole forces panels to orient nearly vertically to catch the slow arc of the sun across the horizon, which means mechanical tracking systems are themselves vulnerable to dust and temperature. The pattern is consistent. Every system required to keep the base alive creates its own maintenance burden. Every solution demands something from every other system. Power needs dust management to keep solar panels and radiator surfaces clear. Dust management needs power to run electrodynamic shields and cleaning systems. Thermal control needs power and radiator surfaces to function. Radiator surfaces need dust management and must survive thermal cycling. Life support needs power and filtration systems. Filtration degrades from dust infiltration and requires replacement parts that must have been launched from Earth and stored. Every node in the web pulls on every other node. A failure in one area does not stay contained. It flows outward through the connections. Power is the hub. It is what the web depends on. And the most demanding moment for that hub, the long shadow period when solar input drops to nothing, is the moment when nothing can be allowed to fail. That web of dependencies and what it means for the people who will have to manage it from inside a base, with no resupply window, is where the hardest questions about long-term lunar habitation are still waiting for answers. Those answers are coming, but the threats that will shape them are not the ones described so far. Everything covered in the preceding sections has a physical presence. Dust coats a visor. A temperature reading drops on a display. A pressure gauge ticks downward. You can see the evidence. You can point to it. The threats that follow work differently. They move through tissue without announcement. They accumulate inside materials where no inspection can reach. They appear in spreadsheets as small shortfalls that compound quietly, over months, until the margin disappears. They are not events. They are conditions. And they become dangerous only when habitation extends far beyond anything humanity has attempted on the lunar surface. The first of them is radiation. On Earth, the average person receives roughly 2 to 3 millisieverts of radiation per year from natural background sources. A millisievert is a unit of biological radiation dose, the amount of energy deposited in tissue weighted by how damaging that type of radiation is to cells. Airline pilots flying at high altitude, where the atmosphere is thinner and provides less shielding, accumulate around 5 to 6 millisieverts annually. Astronauts aboard the International Space Station receive 150 to 200 millisieverts per year. They are still inside Earth's magnetic field, which deflects a significant fraction of incoming particles. The ISS number sounds high compared to standing outside on a summer afternoon, but it is the number a permanent lunar base would look back on as manageable. On the unshielded lunar surface, the continuous dose from galactic cosmic rays alone reaches approximately 400 millisieverts per year. Galactic cosmic rays are high-energy charged particles, mostly protons and heavier atomic nuclei, accelerated to enormous speeds by supernova explosions and other violent events across the galaxy. They arrive from all directions, at all times, without warning, without pause. The moon has no magnetic field and no appreciable atmosphere to deflect or absorb them. Nothing stands between a person on the surface and the full cosmic ray flux. That 400 millisievert figure is not a model output waiting for confirmation. In 2019 and 2020, China's Chang'e 4 lander carried a dosimeter to the lunar surface and recorded the first direct radiation measurements ever taken there. The readings matched what transport calculations had predicted. The moon's surface receives roughly 2 to 3 times the radiation dose of low Earth orbit. The number itself requires careful reading. 400 millisieverts per year does not cause immediate illness. Acute radiation sickness, the kind that begins within hours and can be fatal within days, sets in above roughly 700 millisieverts delivered quickly, over a period of hours or days. The galactic cosmic ray dose is chronic. It accumulates at about 46 microsieverts per hour, every hour, without interruption. The danger is not a single overwhelming exposure. The danger is accumulation. An astronaut on the lunar surface for 18 months would accumulate approximately 600 millisieverts. That approaches NASA's career exposure limit. The consequences of reaching or exceeding that limit are not theoretical. They are documented in epidemiological studies and particle beam laboratory research. Elevated cancer risk, increased probability of cataracts, potential damage to the central nervous system, cardiovascular degeneration, and possible heritable effects. These are not worst-case projections. They are the established biological outcomes of prolonged high-energy radiation exposure to tissues that evolved under Earth's protective shield. But galactic cosmic rays are the predictable component. They are steady, they are measurable. You can model them, account for them, build against them. The unpredictable component is far more dangerous. Solar particle events occur when the sun ejects massive bursts of energetic protons during solar flares or coronal mass ejections. The sun produces these eruptions sporadically, driven by the chaotic behavior of its magnetic field. They cannot be reliably predicted more than a few hours in advance. A modest event might deliver dose equivalent to a few additional days of galactic cosmic ray exposure. A major event is something else entirely. In August 1972, between the Apollo 16 and Apollo 17 missions, the Sun produced one of the most intense solar particle events ever recorded. The timing was fortunate. No crew was on the surface. An unshielded person on the lunar surface during that event would have received several sieverts within hours. A sievert is 1,000 millisieverts. Several sieverts delivered quickly is a lethal dose. The Apollo 17 crew was not on the surface. They were on Earth. Had the timing been different, had the event arrived while they were conducting a moonwalk, they would likely have died. This is not a historical footnote. It is a design requirement. A permanent base must have a dedicated radiation shelter accessible to every crew member within minutes of an SPE warning, not within the hour, within minutes. And that shelter must provide enough shielding mass to reduce the dose from a major event to survivable levels. Most engineering analyses converge on roughly 80 centimeters of lunar regolith, or equivalent mass in another material, as the minimum thickness needed to attenuate the most dangerous components of a large solar particle event. That thickness also meaningfully reduces the chronic galactic cosmic ray dose, though it cannot eliminate it. The highest energy cosmic rays can penetrate meters of solid material. Shielding is mitigation, not elimination. 80 centimeters sounds workable. The reality is different. Providing 80 centimeters of regolith coverage over a habitat means either burying the structure or piling the material on top. Burying a habitat requires heavy excavation, conducted in vacuum, in dust, across extreme temperatures, with equipment that is itself subject to all the degradation pressures already described. Piling regolith on top means moving hundreds of metric tons of material with machinery that has never been operated at any scale on the lunar surface. Both approaches are physically feasible. Neither is simple, neither has been demonstrated. The engineering answer is clear. The operational path to reaching it is not. And there is a subtlety that makes lunar radiation harder to manage than radiation in deep space. When galactic cosmic rays strike the lunar regolith, they do not simply stop. They interact with the atoms in the soil through nuclear reactions, producing secondary radiation, neutrons and gamma rays that scatter outward from the impact point. This secondary radiation does not come only from above. It comes from below and from the sides. A crew member standing on the surface is being irradiated from the sky and from the ground simultaneously. A habitat sitting on the surface receives secondary neutron flux through its floor. Shielding the roof and walls is not enough. The floor must also be shielded, or the habitat must be elevated above the surface with sufficient clearance to reduce the ground level flux, which introduces structural and thermal challenges of its own. The exact contribution from secondary neutrons depends on the mineral composition of the regolith at the specific site, and that composition varies from location to location across the lunar surface. It is an active research area. The numbers are still being refined. What is already clear is that a base designer cannot treat the ground as neutral. Radiation does not confine itself to human tissue. It interacts with every other material in the base. It degrades polymers, accelerating the embrittlement of seals and gaskets that thermal cycling and vacuum chemistry are already attacking. It reduces the efficiency of solar panels over time, compounding the power budget problem, and it causes what engineers call single-event upsets in electronics. A high-energy particle strikes a transistor and flips a bit. A single flipped bit can produce a software error. In some configurations, it can cause a hardware malfunction. These events are random, unpredictable, and continuous. Radiation-hardened electronics exist. They are built to withstand this environment. They are also heavier, more expensive, and less capable than commercial components. A base relying on commercial off-the-shelf parts faces higher radiation-induced failure rates over time. A base using fully hardened components carries those performance and mass penalties everywhere else. There is no version of this trade-off that is free. Radiation on the moon is not something that can be resolved during the construction phase and set aside. It is not a problem with a solution date. It is a condition that presses on human tissue and electronic components and polymer seals every hour of every day, from the moment the first crew arrives to the moment the last one departs. Managing it requires mass, infrastructure, and constant operational attention, and radiation is only the first of the quieter threats. The machines are not the only things being worn down. Radiation presses on electronic components and polymer seals, as the previous section established. But it presses on something else too. It presses on the people inside. And what the radiation does is only part of the story. The gravity itself, the specific fraction of Earth's pull that defines every movement on the lunar surface, introduces its own set of unknowns. Unknowns that no amount of ISS data can resolve. Unknowns that can only be answered by placing people on the moon for months and watching what happens to them. The moon's gravity is approximately 1/6 of Earth's, not zero, not the near weightlessness of low Earth orbit, something in between. And that middle ground is, medically speaking, a blank. Decades of research aboard the International Space Station have given us a detailed picture of what happens to the human body in microgravity. Bone density falls at roughly 1 to 2% per month. The loss is not spread evenly. It concentrates in the weight-bearing bones, the spine, the pelvis, the legs, the structures that normally carry a person's full weight against Earth's pull. Muscle mass declines despite daily exercise. The cardiovascular system reorganizes itself because the heart no longer needs to pump blood upward against full gravity. Fluid shifts toward the head. The heart gradually atrophies. Vision degrades in a significant fraction of astronauts. The mechanism is elevated intracranial pressure, pressure inside the skull that the body cannot regulate properly in the absence of normal gravitational drainage. Researchers call this spaceflight-associated neuroocular syndrome, or SANS. It can cause lasting changes to the structure of the eye and the optic nerve. The immune system shows measurable suppression. Wound healing slows. These are not hypothetical projections. They are documented, confirmed, repeatable observations from hundreds of hours of study on dozens of astronauts. ISS crews mitigate these effects through exercise. Roughly 2 hours per day, every day, on resistance equipment and cardiovascular machines, specifically designed to impose mechanical loading on the body. 2 hours out of every 8-hour workday, before any other task begins. Now here's the question that matters for a lunar base. Does 1/6 gravity protect the crew from these changes? The honest answer is that nobody knows. No human being has ever spent more than 3 days in 1/6 gravity. 3 days. The entire Apollo program, 12 moonwalkers across 6 missions, none of them stayed longer than that. Everything in the medical literature comes from 2 regimes: full Earth gravity and near-zero orbital weightlessness. The space in between, the partial gravity zone where a permanent lunar crew would actually live and work, has never been studied. It is not an area of limited data. It is a medical blank. Physiological models suggest that 1/6 gravity would slow the rate of bone and muscle loss compared to microgravity. Walking on the moon imposes roughly 1/6 the skeletal stress of walking on Earth. The bones are loaded, but lightly. Whether that reduced loading is sufficient to maintain bone density over months and years, or whether it merely slows the decline to a rate that is still dangerous over a long rotation, cannot be determined from models alone. The models have never been validated in this regime because no one has ever lived in this regime. And the answer matters more than it sounds. If 1/6 gravity proves insufficient, the response is not simply to adjust a protocol. The response requires hardware. Exercise equipment capable of imposing Earth-level mechanical loading in a 1/6 gravity environment. Possibly centrifuge systems that generate artificial gravity by spinning a section of the habitat, forcing the body to experience a simulated gravitational pull closer to what it evolved under. These systems are not small, they are not light. They add mass, volume, power draw, and mechanical complexity to a habitat that is already counting every kilogram and every watt with extraordinary care. And the uncertainty about whether they are needed at all cannot be resolved before the base is built. It can only be resolved by building the base and finding out. Meanwhile, whether or not centrifuge systems are required, the exercise burden remains. 2 or more hours per day per crew member, minimum. On a 4-person crew, that is 8 or more crew hours per day spent on mandatory biological maintenance. 8 hours that are not available for dust management, for seal inspection, for construction, for science, for the 100 other tasks that keep the base alive. The time is not optional. Skip it long enough and the crew begins to fail physically. The gravity will not relent simply because the maintenance schedule is full. There is a second dimension to crew health that compounds everything else, and it is harder to engineer against. Psychological health is not separate from biological health. It is part of it, and it degrades on a timescale that matters. Apollo astronauts spent 3 days on the lunar surface. They had constant real-time communication with Earth. They knew exactly when they were coming home. The ISS crews who have spent 6 months in orbit have their own stressors, but they have real-time contact with family, windows that frame the full disk of Earth below them, and a resupply chain that can deliver personal items from home. These are not trivial comforts. They are psychological anchors. A crew living on the moon for months would have none of that in the same form. Earth would be visible as a small disk in the sky, not a world filling the window. Communication delay is approximately 1.3 seconds round trip, technically close to real time. But communication delay is not the measure of psychological distance. The measure of psychological distance is evacuation distance. If something goes wrong, if a crew member becomes seriously ill or injured, if a psychological crisis reaches a breaking point, the minimum transit time to bring that person home is 3 days. Not 3 hours. 3 days, requiring a rescue mission to be staged, launched, and executed. The crew lives inside that knowledge every day. The distance is not 1.3 seconds. The distance is 3 days minimum, and every person on the surface understands that. Confinement inside a small pressurized volume for months. Repetitive, physically demanding maintenance tasks where a single error can be lethal. Chronic danger that cannot be set aside or declared over at the end of a shift. These conditions have analogues in human experience. Antarctic winter overstations, where small teams are isolated in extreme environments through polar night with no possibility of evacuation for months, show documented rates of depression, cognitive decline, sleep disruption, and interpersonal conflict that increase with the length of the stay. Submarine deployments produce similar patterns. Both are studied carefully by space medicine researchers because they are the closest operational analogues available. Neither is as extreme as months on the lunar surface. Both produce measurable psychological degradation. The lunar environment would begin where those analogues end, and then all of it compounds. A crew member who is losing bone density at an uncertain rate, accumulating radiation dose every hour, managing trace dust contamination in the habitat air, sleeping poorly under chronic low-level stress, and spending 2 hours every day on mandatory exercise, is not operating at the capacity of a healthy person in a normal environment. Cognitive performance falls under chronic sleep disruption. Decision-making degrades under prolonged stress. Physical capability declines as musculoskeletal deconditioning progresses. These are not extreme projections. They are the documented downstream effects of the conditions that a lunar base crew would live inside, continuously, for the entire rotation. The base does not need to keep the crew alive. That framing is too simple. The base needs to keep the crew performant. Alive but cognitively degraded is not sufficient. Alive but physically depleted is not sufficient. The life support systems, the power infrastructure, the dust management protocols, the SEAL inspection routines, all of it requires people who can think clearly, move effectively, diagnose problems correctly, and execute solutions under pressure. If crew effectiveness degrades faster than anticipated, the maintenance burden that was already difficult becomes impossible. The machines are breaking down. The people maintaining them are breaking down. Both are degrading inside the same environment at the same time. That is not a problem with a scheduled solution. It is a condition that deepens with duration, compounding every other risk the base is already carrying. And the biological burden on the crew is only the second of the quieter threats. That third threat compounds both of them. Now follow both of them into the actual work waiting to be done. Every mechanical system has a designed operational life. Engineers calculate how many cycles a valve can complete before its seat wears down, how many hours a pump can run before its bearings degrade, how many thermal expansions and contractions a seal can survive before it no longer seals. Those calculations assume something. They assume the system operates in conditions close to the ones it was designed and tested in. On Earth, that assumption holds. On the Moon, it fails from the first day of operation, and it never recovers. The ISS Environmental Control and Life Support System, the ECLSS, is the closest analog humanity has ever built to what a lunar base would need. It processes urine and condensed humidity into drinkable water. It splits water into oxygen and hydrogen to keep the crew breathing. It scrubs carbon dioxide from the cabin air before it reaches toxic concentration. Each of those functions is a separate assembly, with its own pumps, valves, filters, chemical beds, and maintenance requirements. Together they keep 6 or 7 people alive in a sealed metal cylinder in a vacuum. Here is what that actually demands. The water recovery system distills wastewater through a rotating drum assembly, runs the output through a catalytic reactor that purifies it with a chemical bed requiring periodic replacement, and circulates the result through fluid lines and valves that need regular servicing. Throughout the station's operational life, that assembly has experienced repeated pump malfunctions, separator drum failures, and contamination events serious enough to force the crew onto backup water stores while engineers on Earth work through recovery procedures. Some of those procedures took weeks. The oxygen generation system electrolyzes water, splitting it into oxygen for the crew and hydrogen as a byproduct. The cell stack at the core of that process degrades and must be replaced. The hydrogen must be managed. Some is vented. The rest is fed into the Sabatier reactor, which combines it with carbon dioxide to reclaim additional water. The Sabatier reactor has its own maintenance schedule, its own failure modes, and its own history of crew interventions. The carbon dioxide removal assembly cycles chemically active beds between scrubbing and regeneration, drawing power and producing waste heat each time a bed regenerates. The valves that switch the flow between beds have failed repeatedly across the station's history. Each time, the crew improvised a workaround while waiting for replacement parts on the next resupply vehicle. All of that across all three systems, inside an environment that is not the moon. No dust, no regolith abrading pump seals or clogging filter media from outside. Milder thermal cycling. No electrostatic contamination drifting through every airlock transit. The ISS operates in conditions a lunar base crew would consider forgiving. And the ISS crew still devotes 25 to 40% of working hours to maintenance and repair. During heavy periods, above 50%. More than half of every working day going to keeping the station functioning, leaving what remains for the science that justifies the station's existence. And the reality is worse. That number, which already seems high, is a floor for what a lunar base would face, not a ceiling. Every one of the same life support functions operates on the moon, in an environment that accelerates the degradation of every component. Lunar dust infiltrates every airlock transit regardless of protocol, clogging air filters faster than any tested replacement schedule accounts for. Regolith particles contaminate water processing lines. Abrasive particulates reach valve seats and pump seals that were not designed to operate in their presence, wearing surfaces faster and in different patterns than the failure models predict. Electronics throughout the habitat experience higher rates of radiation-induced errors, accumulating single-event upsets that require monitoring and correction. The lunar crew doing all of this is 4 to 6 people. The ISS crew doing it in a more forgiving environment is 6 to 7. And unlike the ISS, a broken component cannot be returned to Earth for engineering analysis. It cannot be replaced faster than the next resupply mission. Whatever failed is either repaired in place, improvised around, or added to a growing list of degraded systems the crew is managing but not resolving. And the lunar base adds an entire category of maintenance that the ISS largely avoids. External maintenance, solar panels, thermal radiators, communication antennas, rover mechanisms, construction equipment. All of those systems sit outside the habitat, exposed continuously to dust accumulation, thermal cycling, and radiation degradation. Inspecting them requires an EVA. Servicing them requires an EVA. Every EVA imposes its own costs. Suit wear, airlock cycling, additional dust ingress when the crew returns, accumulated radiation dose. Internal maintenance and external maintenance do not run in parallel. They compete for the same finite pool of crew hours. Every hour spent outside cleaning a solar panel is an hour not spent inside replacing a filter or servicing a valve. Month 8 of base operations. The scenario is concrete. A valve in the carbon dioxide removal assembly begins sticking intermittently. The crew notices rising CO2 levels during sleep periods, traces the source, confirms the valve. Replacing it requires partial disassembly of the removal assembly. 2 crew members. Approximately 6 hours. During those 6 hours, the base operates on backup CO2, scrubbing at reduced capacity. To keep carbon dioxide within safe limits, the crew must reduce physical activity throughout the base. The other 2 crew members cannot perform a scheduled EVA to clean the solar panels. The base cannot afford anyone exerting at full capacity, producing more CO2 than the backup system can handle. The panels go uncleaned. For 3 additional days, they accumulate dust, and their output drops a few percent. That reduction shrinks the power margin available for thermal management. The following week, a secondary coolant pump shows elevated vibration during operation, bearing wear consistent with accelerated thermal cycling. The crew must prioritize that pump. They do so knowing the solar panels are still running below capacity and that if the pump fails completely, the coolant circuit it serves could cascade into a thermal shutdown. Every choice forecloses another. Every repair displaces a task that was already scheduled. The backlog grows, not slightly, non-linearly. Systems that operated without issue through the first 6 months begin showing wear at 9. By 12 months, multiple systems need attention at the same time, and the crew is deciding between failures rather than preventing them. By 18 months, the earliest components approach the end of their designed operational lives, requiring a replacement or accepted degradation. The crew is always behind, fixing last week's failure while this week's approaches its threshold. There is no moment when the maintenance backlog clears and the crew gets ahead of the schedule. The schedule is the condition, and spare parts cannot be wished into existence. A failed pressure seal cannot be improvised from materials available in a habitat. A degraded solar cell cannot be repaired with tools a crew member carries. Carrying sufficient spares for every critical system across a multi-year occupation requires either an initial payload so large it strains every launch constraint, or resupply missions frequent enough to keep the shelves stocked. Research into manufacturing spare parts from lunar regolith using 3D printing systems is active and serious. It is also far from operational. The gap between demonstrating that a process works in a laboratory and relying on it to produce a replacement pump seal during a life support failure is not a gap that closes on a schedule. On a remote Antarctic station, a maintenance backlog means delayed science, damaged equipment, reduced comfort. Inconvenient. On the moon, the same backlog is something qualitatively different. The systems accumulating in that backlog are the ones keeping 4 people alive. A coolant failure is not an inconvenience. A CO2 scrubber running at partial capacity for a week while the crew waits for a valve replacement is not a delay. Both are how a crisis begins. The biological burden was the second of the quieter threats. The maintenance cascade is the third, and none of these 3 have finished interacting with each other. Every repair so far has assumed the part would arrive. The crew orders what breaks, the manifest is filed, the mission is planned, and somewhere, 240,000 miles away, the supply chain does its work. That chain is everything. A permanent lunar base cannot produce most of what it consumes. Not yet, and not for years. Food travels that chain, medical supplies travel it, replacement filters, spare pump assemblies, circuit boards, valve seats, batteries, clothing, drill bits, cable connectors, oxygen generation membranes, CO2 removal bed material, personal items small enough to keep a crew psychologically intact across months of confinement. Everything the base cannot make for itself has to come from Earth, cross 240,000 miles of vacuum, and land intact at the lunar South Pole. And the cost of moving anything across that distance is staggering. Launching 1 kilogram of payload to the lunar surface currently costs somewhere between hundreds of thousands and over $1 million, depending on the launch vehicle and the lander. A modest resupply mission delivering a few hundred kilograms of critical supplies represents a roughly $100 million operation. It requires months of planning, component integration, launch scheduling, transit, and a precision landing on terrain that has already claimed multiple landers in the 2020s. A base consuming several metric tons of consumables and spares each year needs multiple missions annually. Each one is an independent event. Each one can fail. There is no warehouse on the moon. There is no secondary supplier nearby. No backup delivery service. If a resupply mission fails at launch, which is a non-trivial probability even for reliable rockets, the base receives nothing. If it fails during landing, which has happened, the base receives nothing. The next window may be 4 months away. Think about what that means in terms of raw consumption. ISS data gives us a baseline. Each astronaut needs roughly 1.5 kilograms of food per day. 4 crew members over a full year requires around 2,200 kilograms of food alone, assuming no local production. Water recycling on the ISS recovers about 90% of water used. The remaining 10% is lost and must be replaced, amounting to several hundred additional kilograms per year for a 4-person crew. Air losses from airlock cycling, minor habitat leaks, and system consumption add hundreds more kilograms of oxygen and nitrogen annually, unless local production is fully operational. Then add the consumable life support components, dust filters with service lives measured in weeks, CO2 removal beds, water purification catalyst cartridges, oxygen generation membranes. Add mechanical spares, pump impellers, valve seats, seals, bearings, electrical connectors, circuit boards, sensors. The annual manifest for a base of 4 people runs to thousands of individual critical line items. NASA's planning envisions resupply roughly every 6 months using commercial lunar landers, each carrying a few hundred kilograms. For the consumption rates described above, that means roughly 4 resupply missions per year, each one an independent opportunity for failure. Here is where the math becomes uncomfortable. If 4 resupply missions per year each carry a 5% failure probability, the chance that all 4 succeed in a given year is approximately 81%. Over 5 years of operations, the cumulative probability of experiencing at least 1 mission failure approaches 65%. Not a theoretical edge case, not a remote contingency. A statistical near certainty across any multi-year campaign. A resupply failure is expected. The question is only when. To understand what that means in practice, consider what the base looks like in month 14. The most recent resupply mission was carrying replacement HEPA filters for habitat dust filtration and a spare pump assembly for the water recovery system. During landing, the descent engine underperforms. A fuel valve malfunction, possibly. The lander impacts at a speed that destroys its payload. The base receives nothing. The next resupply window is 4 months away. The existing HEPA filters are already past nominal service life. They were not overdue by much, but they were running long. Dust concentration in the habitat air begins to rise. The crew can reduce EVA frequency to limit how much dust they track in through the airlock, but that halts external maintenance and ongoing construction. And the water recovery pump that was already showing early bearing wear continues degrading without the spare assembly that was supposed to replace it. The crew is now managing declining air filtration and a degrading water system simultaneously, with no replacement parts available for either. They can restrict water use to extend the pump's remaining life. They can wear respiratory masks inside the habitat to reduce dust inhalation. These are survivable measures in the short term. Over 4 months, they are physically and psychologically punishing in ways that are difficult to fully convey, and they accept a level of ongoing health risk that no space agency has ever deliberately imposed on a crew as a planned operational condition. But here's where it gets strange. The moon is often cited as a near destination. We can reach it in 3 days. Compared to 9 months for Mars, that sounds like safety. 3 days is not 3 hours. An emergency on the International Space Station in low Earth orbit can be resolved by returning crew within hours using already docked escape vehicles. A lunar emergency requires 3 days minimum for any response, and that assumes a rescue vehicle is fueled, staffed, and ready for immediate launch. It almost certainly would not be. In practice, an organized emergency response to the lunar surface would more likely take weeks. The crew survives on their own resources until help arrives, or they do not survive. The 3-day transit is a genuine advantage over Mars. It is not proximity. It is not rescue. What the month 14 scenario illustrates is not just the fragility of a single supply chain. It is something broader, and it is the pattern that makes a permanent base qualitatively different from anything humanity has attempted before. The threats described across this account are not independent. They interact. They feed each other. Dust degrades seals. Degraded seals leak. Leaks consume air reserves faster than planned. Higher air consumption increases resupply demand. More resupply missions means more failure opportunities. Each interaction generates pressure somewhere else in the system. Thermal cycling fatigues. Structural joints. Fatigue joints require inspection. Inspection requires crew time. Crew time spent on inspections is crew time not spent on other maintenance. The backlog grows. Radiation degrades electronics. Degraded electronics malfunction. Malfunctions produce repair tasks. Repair tasks consume spare parts. Spare parts must be resupplied. Resupply missions occasionally fail. Human health declines from radiation accumulation, bone loss, dust inhalation, sleep disruption, and chronic low-level stress. Declining health reduces crew effectiveness. Reduced crew effectiveness means maintenance tasks take longer. Longer maintenance tasks compete with the 2 hours per crew member per day of mandatory exercise that exists to slow the decline in the first place. Every burden feeds every other burden. The system does not plateau. It generates new problems continuously from the interactions of existing ones. A short mission avoids this entirely. You land, perform your assigned tasks, and leave before the interactions have time to develop. The Apollo program was brilliant precisely because it departed before the compounding began. Permanence means something different. It means living inside the compounding every day for years, with no option to declare the experiment complete and come home. The resupply fragility is the fourth of the deeper threats, and it is not the last thing that needs to be understood about what the base is being asked to sustain. The engineers are not blind to any of this. The people designing Moonbase 1 have read the Apollo reports, modeled the thermal cycles, and mapped shadow periods at every candidate site down to individual boulders. They have calculated radiation dose rates and stress-tested their habitat designs against the pressure differentials described in earlier sections. The solutions they propose are real. They are grounded in physics. Many are already in development. The question is not whether each solution is reasonable. The question is what each one costs, and whether the total cost of all of them together, implemented simultaneously in the same hostile environment with the same constrained crew, adds up to something human institutions can actually sustain. Start with the strongest argument for the South Pole. Permanently shadowed craters near the lunar South Pole contain water ice, accumulated over billions of years from comet and asteroid impacts. If that ice can be mined and processed, a base can produce its own drinking water without launching it from Earth. Electrolysis can then split the water into oxygen for the crew to breathe, and hydrogen that can be stored as rocket fuel. A base that generates its own water, air, and propellant becomes dramatically less dependent on resupply from Earth. This is the central logic of NASA's long-term strategy. It is called ISRU, In Situ Resource Utilization, meaning using what the environment already provides rather than carrying everything from home. In principle, it is the closest thing to a genuine solution for the supply chain problem described in the previous section. But the picture does not hold. The ice sits in craters where temperatures hover near negative 200 degrees Celsius. That is not just cold in the way that an Antarctic winter is cold. That is within a few dozen degrees of absolute zero, the threshold where atomic motion itself nearly stops. Conventional lubricants solidify completely at those temperatures. Batteries lose most of their charge capacity. Metals embrittle and crack under mechanical stress. Electronics fail as solder joints contract, and circuit substrates fracture. Any machine sent to mine that ice must either carry its own heat source, requiring power, or be built from exotic materials that maintain function at near deep space temperatures, adding mass and cost with every component. The ice itself presents its own complications. It is not a frozen lake waiting beneath a thin crust. Orbital observations suggest the ice exists as thin molecular deposits mixed unevenly into the upper layers of the regolith, possibly concentrated in pockets, but distributed across crater floors without the clean uniformity that would make large-scale extraction straightforward. Extracting usable quantities may mean excavating and heating enormous volumes of regolith to liberate water vapor, then capturing and condensing that vapor in vacuum conditions where water does not exist as a liquid at any temperature. The processing equipment must handle abrasive, electrostatically charged feedstock without clogging, jamming, or wearing down reliably at a scale supplying hundreds of liters of water per month. No such system has been tested on the moon. The engineering is plausible, the operational reality is unproven. And then the sequencing problem appears. You need power to mine the ice. You need the ice to reduce resupply dependence. You need resupply to deliver the power systems in the first place. Each capability depends on the others being in place before it can function. The solution requires itself to exist before it can be built. Regolith shielding carries a similar structure. Roughly 80 centimeters of regolith piled over a habitat reduces radiation exposure to levels permitting longer occupancy, and the moon's surface is covered in regolith, so there is no shielding material to launch from Earth. That is genuinely attractive, but 80 centimeters over a habitat module, several meters wide and more than 10 meters long, is dozens of metric tons of material to excavate, transport, and place with sufficient precision for uniform coverage without damaging the structure beneath it. That work requires construction equipment, excavators, haulers, placement mechanisms capable of operating in vacuum, thermal extremes, and pervasive abrasive dust. That equipment must be launched, landed, deployed, and commissioned before any shielding work begins. Each piece is subject to the same degradation mechanisms, wearing down every other surface system. Some researchers propose sintering, using focused solar or microwave energy to fuse loose regolith into solid structural blocks. Laboratory tests with lunar simulants show genuine promise. Sintered blocks are structurally sound, provide radiation shielding, and offer thermal insulation. But sintering equipment must be designed for the lunar environment, consumes significant energy, and produces blocks slowly enough that covering a full habitat module takes months. And sintering does not eliminate dust. It reorganizes some of it into blocks, while the excavation and handling process generates additional fine particles. The dust problem is not solved. It is rearranged. Robotics offer a different answer. The logic is straightforward. If the environment is too hostile for continuous human exposure, use robots for the most dangerous and repetitive tasks. Robotic excavators can pile shielding. Robotic rovers can inspect external systems and clean solar panels. NASA's Phase 1 plan is built around exactly this premise, using robotic precursor missions to test these capabilities before any crew arrives. Wait, robots on the moon face every physical challenge the hardware faces in that environment, minus biological vulnerabilities, plus their own. Robots require power and communication links. Earth-based teleoperation involves a round-trip signal delay of approximately 2.5 seconds, which makes real-time control of delicate tasks genuinely difficult. Autonomous operation requires software sophisticated enough to handle unpredictable terrain, unexpected equipment states, and novel failure modes without human judgment in the loop. That level of autonomy exists in controlled factory environments. It is far more limited on an unstructured lunar construction site where the unexpected is routine. And robots also suffer from dust. Their joints stiffen as lubricants degrade. Their sensors become occluded. Their electronics experience radiation-induced errors. Their batteries lose capacity in cold. A robot that needs human maintenance every few weeks is not solving the labor problem. It is returning it to the crew in a slightly different form. The net gain is positive. It is just smaller than intuition suggests, and it depends on a reliability that Phase 1 missions are designed to measure, but have not yet measured. Nuclear power is the most credible answer to the energy problem. A fission reactor, such as NASA's Kilopower program and its successors, could provide continuous power through shadow periods regardless of sun angle, with enough capacity to run life support and ice mining simultaneously. That would cut through the sequencing problem that ice extraction alone cannot resolve. The constraints are easy to overlook. The reactor requires a radiation exclusion zone of roughly 90 meters. That means power must transmit across that distance through cables or wireless systems exposed to the surface environment. The reactor must be cooled, and in vacuum, that means radiator panels that reject waste heat while surviving years of dust accumulation, thermal cycling, and micrometeorite impacts. If dust cuts the radiator's efficiency, the reactor must reduce output or risk overheating, and maintaining reactor cooling becomes one more entry on the maintenance schedule. A single reactor is a single point of failure. Deploying multiple units multiplies the mass cost and the maintenance burden. And if the reactor fails during a shadow period, when solar power is unavailable, the base loses power for life support. Backup batteries must bridge that gap, not redundant insurance. A structural requirement that partially negates nuclear power's mass savings advantage. Then, there is the programmatic reality. Launching a nuclear fission reactor requires political approval, regulatory compliance, and public acceptance that is not guaranteed even when the technical case is sound. RTGs, the smaller radioisotope thermoelectric generators that have powered deep space missions for decades, have generated public scrutiny at every launch. A fission reactor is a larger step both technically and politically. Approval delays could push the power solution past the timelines the rest of the base plan depends on. Phased construction, building incrementally, and testing each system before committing human lives is itself a form of solution. It is sound engineering. It respects that lunar operations involve unknowns that only experience can resolve. Phase 1 establishes robotic precursors. Phase 2 deploys infrastructure. Phase 3 brings sustained habitation. Each step informs the next. That is the right way to build something in an environment this unforgiving. But look at what happens when you add the costs together across all 5 solutions. Each one is individually reasonable. Each addresses a real problem with a real engineering approach. And each costs something: mass to launch, power to generate, crew time to allocate, complexity to manage. The base does not merely need a habitat. It needs a habitat plus a power plant, plus a radiation shelter, plus dust mitigation systems, plus thermal management infrastructure, plus ice mining equipment, operating at negative 200 degrees Celsius, plus construction robots navigating 2.5-second teleoperation delays, plus maintenance infrastructure for all of it, plus a resupply chain, plus medical facilities, plus communication relays, plus rovers, plus spare parts for every subsystem, plus the crew time to operate and maintain all of it simultaneously. That is what a moon base actually is, not a building. A machine, hundreds of subsystems, each dependent on the others, each under continuous environmental attack, each competing for the same constrained pool of power, crew time, and resupply mass. The ice mining system needs the nuclear reactor. The nuclear reactor needs the radiator panels. The radiator panels need cleaning. Cleaning requires EVAs. EVAs wear out suits and airlock seals. Worn seals need replacement. Replacement parts come from resupply. Resupply occasionally fails. Keeping this machine running is not a one-time engineering achievement. It is a continuous operational commitment that never ends for as long as the base is occupied. And there is one more vulnerability threaded through all of it that the engineering solutions, individually, cannot address. That vulnerability is not a materials problem. It is not a power problem. It is not a dust problem, or a radiation problem, or a supply chain problem. Each of those has an engineering answer, however costly. The last vulnerability has no engineering answer at all. It is a political one. Phased construction depends on time, a decade of it, and time is not neutral. It is a medium in which political will degrades, just as surely as seals degrade and lubricants break down under vacuum. The plan stretches across multiple election cycles, through annual budget negotiations with a Congress that has never treated space exploration as a stable funding priority, past commercial partners whose financial survival depends on government contracts continuing, and through the aftermath of any high-profile failure that could trigger a political retreat. Every one of those dependencies must hold, simultaneously, for 10 years. This is not a hypothetical risk. It has happened before. In 2004, NASA announced the Constellation program. The goal was to return humans to the moon by 2020 using a new family of vehicles. 2 rockets called Ares-1 and Ares-5, a crew capsule called Orion, and a lunar lander called Altair. Constellation was not a concept study or a paper architecture. It was a funded, staffed, hardware-producing program. Billions of dollars flowed into contracts. Test articles were built. Engines were tested. The program had political support from the administration that announced it, congressional authorization, and a clear technical roadmap stretching across the decade. It looked, from the outside, like a program with momentum. By 2009, 5 years in, an independent review committee assessed the program's status. What it found was uncomfortable. Constellation was significantly underfunded relative to its goals. It could not achieve a crewed lunar landing on any realistic timeline without major budget increases that were not coming. The architecture was sound, the engineers were capable, the hardware existed, but the money and the time no longer aligned. In 2010, the incoming administration cancelled Constellation entirely. The Ares rockets were abandoned. Altair was cancelled. Only Orion survived, repurposed years later for the Artemis program that now forms the foundation of the 2026 plan. Roughly $9 billion of development work had been spent. 5 years of institutional momentum had accumulated. Thousands of engineering careers were redirected or dissolved, and the moon receded from NASA's operational horizon for more than a decade. Not a program that failed technically, one that was cancelled politically after $9 billion with active hardware on the test stands. The parallels to the current plan are uncomfortable. A decade-long phased program, billions in committed funding, commercial partnerships that are financially dependent on continued government contracts, a technical timeline where every phase must succeed before the next can begin, a political environment where priorities shift with administrations, budgets face annual reauthorization battles, and a single high-profile failure can trigger reassessment of the entire effort. Constellation had all of these features. It did not survive them. The 2026 moon base plan's timeline extends through at least 2 presidential administrations, beyond the one that initiated it. If any administration in that span decides to redirect funding toward a Mars program, toward commercial space stations, toward deficit reduction, or toward any other priority competing with a multi-billion-dollar lunar infrastructure commitment, the base could stall exactly as Constellation did. Partially built, enormously expensive, ultimately abandoned. Hardware already landed on the surface would sit unused, degrading under the same dust and thermal cycling and radiation described throughout. Commercial partnerships would dissolve, engineering teams would disperse. The next attempt would start not from where this one stopped, but from a position weakened by public skepticism about whether this was ever achievable. But the comparison is not symmetric. The International Space Station survived its multi-decade construction timeline despite cost overruns, schedule slips, technical crises, and multiple changes in American political leadership. It survived because it had an anchor. The station's bipartisan political support in the United States was reinforced by the geopolitical relationship with Russia. International partnership created mutual accountability. Cancellation would have meant abandoning a commitment to allies. It would have had diplomatic consequences, not just programmatic ones. That cost made cancellation politically expensive in ways that purely domestic programs are not. The moon base does not yet have an equivalent anchor. International partners are mentioned in NASA's plans. Several nations have expressed interest. Agreements have been signed, but no binding international commitment of ISS scale exists. There is no partnership structured so that cancellation would rupture a geopolitically significant relationship. The program currently depends on domestic political will, sustained across a decade, in a country with a historical record of cancelling decade-long space infrastructure programs when administrations change. The ISS anchor was not incidental. It was structural. It was the reason the station exists today. Without something equivalent for the moon base, the program carries the same vulnerability that destroyed Constellation, and no engineering solution addresses it, because it is not an engineering problem. Consider what interrupted funding would actually mean at year 4 or year 6 of the construction sequence. Not a clean cancellation with a clear endpoint. A slow withdrawal, budget reduced, but not eliminated. Milestones slipping, commercial partners scaling back, contracts not renewed, key personnel moving to other programs. The half-built base sitting on the lunar surface, its systems degrading, its robotic infrastructure going unmaintained, its supply chain attenuating until a formal announcement acknowledges what has been functionally true for a year or two already. The hardware does not wait for the political decision. It begins deteriorating the moment maintenance stops. This is the vulnerability the engineering solutions cannot reach. You can design a better seal, you can develop a more efficient nuclear reactor, you can engineer dust mitigation systems and redundant life support and radiation-hardened electronics, but you cannot engineer sustained political will across a decade of changing administrations, budget cycles, and competing priorities. That is a different kind of system, and the historical record suggests it is at least as fragile as the SEALs. The Constellation program demonstrated that a well-funded, technically active, congressionally authorized lunar program can collapse in the space of one administration change. $9 billion did not protect it. Active hardware did not protect it. 5 years of institutional momentum did not protect it. What it lacked was the anchor. And the 2026 plan, as it stands, lacks it too. The engineering challenges described throughout are genuine. The political challenge may be the hardest one of all. Set physics and politics side by side, and the picture that emerges is not a technical program with some political risk attached. It is a permanent commitment to contend with an environment that has never offered anything and never will. To understand the scale of that commitment, consider the hardest thing we already do on Earth. The Amundsen Scott South Pole Station sits at the geographic South Pole in Antarctica. It supports a winter-over crew of roughly 50 people. Temperatures drop below -70 degrees Celsius. 6 months of continuous darkness. Resupply is only possible during the brief Antarctic summer, and the logistics chain that delivers fuel and equipment traverses one of the most demanding supply routes on the planet. Systems fail regularly. The crew spends significant time on upkeep. By any ordinary measure, Amundsen Scott is one of the most demanding logistics operations in human civilization. But the comparison is misleading. That station sits on a planet with breathable air. It has full Earth gravity, which means bones do not thin, and muscles do not atrophy the way they might in reduced gravity. Liquid water exists beneath the ice cap. And if a medical emergency outstrips the station's resources, an aircraft evacuation is possible during summer months. The station is hard. It is not the moon. The moon removes every one of those advantages. The radiation is worse. The vacuum is lethal. The dust is destructive in ways that have no Antarctic equivalent. The gravity is insufficient for long-term health in ways we cannot fully predict. Emergency evacuation is not a matter of hours. It is a minimum 3-day transit requiring a rocket launch from Earth, a precision intercept, and a landing on terrain that has destroyed multiple robotic landers in recent years. The resupply route is not a 1,000-mile traverse across Antarctic ice. It is a 240,000-mile journey through space. Not a harder version of the same problem. A different order of problem entirely. If sustaining 50 people at the Antarctic South Pole is among civilization's most demanding operations, sustaining 4 people at the lunar South Pole is an order of magnitude harder. That comparison is not rhetorical. It is the most honest scale available to us, and even it understates the distance. This is the reality the press conferences do not convey, not because engineers are hiding it. The technical documents are public. The challenges appear throughout NASA's own literature, but the public narrative compresses the difficulty into a single word, something like ambitious or challenging, and moves on to the vision. The vision is genuine. The science a permanent lunar base could produce is extraordinary. The technologies it would develop apply to Mars and beyond. The symbolic achievement is real, but meaning does not reduce difficulty. The two things are separate. A moon base is not a destination you build and then inhabit the way you build a house and move in. A house on Earth exists in an environment that passively supports human life. The air is breathable without intervention. The temperature is survivable without active management every second. The structure holds itself up without fighting continuous pressure, differential, or thermal stress. Nothing is trying to destroy it. A moon base exists in an environment that opposes human life through every mechanism available. The air must be manufactured and recycled. The temperature must be actively managed at all times. The structure must resist decompression under perpetual mechanical stress. The dust must be fought daily. The radiation must be shielded against continuously. The power must never fail. The supplies must keep arriving. The moon is 240,000 miles away. On a clear night, you can see it from your backyard. It looks serene. Apollo proved you can go there and come home safely. One of the greatest achievements in human history. But visiting and living are not the same thing. Visiting means surviving the environment long enough to leave before it defeats your systems. Living means contending with it without end. The environment does not pause. It does not relent. It does not forgive a missed maintenance cycle, a degraded seal, or a supply shipment that failed to launch. The moon feels manageable because it is close. That closeness is an illusion of familiarity. We have looked at it every night of our lives, sent 12 people to its surface and brought them all home, photographed and mapped, and named its craters until it feels known. But known is not hospitable, and close is not easy. The moon turns every ordinary human need into an engineering problem. Breathing becomes a filtration and recycling challenge. Drinking becomes an ice mining and water processing operation. Staying warm becomes a nuclear power and thermal management project. Walking outside becomes a radiation exposure and dust contamination event. Repairing a broken pump becomes a spare parts and crew time crisis. Sleeping becomes a psychological support and circadian rhythm intervention. Nothing is simple, nothing is passive, nothing is free. And the most unsettling truth is this: these problems do not shrink with time, they grow. The longer a base operates, the more its systems degrade. The more they degrade, the more maintenance required. The more maintenance required, the less time available for the science and exploration that justified building it. A base that cannot keep pace with its own deterioration is losing a slow contest against the lunar environment. Winning that contest requires not a single heroic engineering effort, but permanent institutional commitment. Staffing, funding, supplying, maintaining an outpost on a world that erodes everything humans bring to it. That is the true cost. Not $20 billion, though that number is real and probably an underestimate. Not a decade of construction, though that timeline is real and probably optimistic. The true cost is permanent obligation. Sending supplies, replacing components, training crews, funding operations, solving problems the moon generates faster than intuition predicts. The base does not become self-sustaining after construction is complete. Construction is never complete. The base is always under repair, always one system failure from crisis. The 12 astronauts who walked on the moon were the bravest of their generation. They faced risks most people cannot comprehend. They succeeded beyond almost any rational expectation. And they left before the moon could show them what it does to things that stay. They were there for hours. Apollo 17's crew, the longest surface stay, spent less than 3 days on the lunar surface. They departed before the compounding began. That was not a limitation of Apollo. It was its brilliance. A permanent base would learn the lesson Apollo never had to learn. In every cracked seal, every clogged filter, every degraded solar cell, every centimeter of bone density lost over months of reduced gravity, every supply manifest scrutinized for the one missing item that could become a crisis. The moon would teach that lesson slowly and continuously, without ever offering a break. This does not mean humanity should not build a moon base. It means humanity should understand what building one actually requires. Not the version with gleaming habitats and smiling astronauts in bright corridors. The real version, where every day is a steady contest against dust that infiltrates everything. Darkness that drains power, radiation that accumulates in every cell, cold that cracks every seal, and distance that makes every missing spare part a potential emergency. The moon is not waiting to welcome us. It is simply indifferent. And a base there is the one that lives in the physics, not the one in the animations. A permanent commitment to endure on a world that asks everything and forgives nothing. That is what going to stay actually means.